Okay, so in previous video we have seen about the pipelines, right? Instruction pipelines and the conflicts that are possible in instruction pipeline and probable solution that we have also seen. Now the next is a RISC pipeline, right? So the simplicity of instruction in RISC, right? Because the instruction length is fixed, then the load, everything that is operation that is performed based on the after load and store, right? The instruction will not any operation will not fetch data from memory, right? So the simplicity of the instruction can be utilized to implement an instruction pipeline using a small number of sub operation which it can execute in one cycle. So suppose you divide this instruction pipeline in three segments. So this each segment that can be executed in one cycle, right? The second is the decode operation can occur at the same time due to the fixed instruction format, right? So when you decode your instruction, it will occur at the same time. Why? Because we know that we have fixed, or not we, they have fixed the instruction format for RISC, right? First you need to do load and store, then to address instruction, right? And there is no need to calculate effective address or fetching operands from memory. Why? Because that task is performed by load and store instruction, right? Load and store instruction will do that. In load and store also, what it will do, first it will fetch the instruction from memory, then it will load data from memory to your registers, right? This way this load and store instruction will execute, right? Now any other operation that will be based on the register operand only. So in that case we need not to calculate the effective address. Okay, in such instruction load and store is required in load and store, but other instructions don't require that, as data are directly available in registers. Okay, now the next instruction pipeline that can be implemented with two or three segments. So basically these are the three segments. Mhm. Fetch instruction, execute the instruction, and store a result in destination registers. So these three segments are required for pipelining in RISC. Now the data transfer instruction in this are limited to load and store instruction which use register indirect mode. Okay, now to resolve, this is already discussed, right? I have just told you. Now to resolve memory conflicts between fetch instruction and load, store, and operand, right? Because you are fetching the operand as well, you are getting operand from memory to register while you are using load and store. Okay, you are also fetching the instruction as well. So what most of the RISC machine do, it uses two separate buses with two memories. One memory is used to store the instructions and another memory is used to store the data, means your operand. So with these two buses, right, parallelly you can fetch the operands, and in another buses you can fetch the instructions, right? So it will not overlap. So what is the advantage? So advantage of this RISC pipeline is its ability to execute instruction at the rate of one clock cycle, right? Its sub operation is such that the one segment can be executed in one clock cycle, which is difficult in CISC kind of architecture, right? Because in CISC the length is not fixed, there are different addressing modes are available, so it might possible that some segment take more clock, right, 2 or 3 clock, and to that segment every other segment need to match, right? Because then you will get a proper uh, pipeline execution. right? So other segment, right, suppose segment number 3 is taking 3 clock in CISC, segment 1, segment 2, that is taking 1 clock. So that segment 1 and 2 need to wait for other 2 clock cycle as well, right? So it will not give you that good performance. So but the risk as instruction length is fixed, right? Data are in machine register only, right? So they can perform the task that is in one segment at one clock cycle, right? So once you perform that segment task in one clock cycle, and we are using pipeline approach, so what uh, we will achieve, we will achieve that we are executing each instruction in the one clock cycle, right? But remember that first instruction will take 3 clock if there is a 3 segment and each segment is taking 3 clock cycle. Then the first instruction will take 3 clock. After that, at each clock you can execute your instruction, right? And another advantage is support given by the compiler, which detects and minimize the delays encountered due to the data conflicts and branch penalties, right? So the compiler, right, I think whatever doubt you have, this is the answer. So the support given by the compiler which detects and minimize the delays encountered due to the data conflicts, means data is not available, and your branch penalties, there is a branch, okay? So in this case your compiler will support this in RISC kind of architecture. Let's see this for delayed data conflicts. So 3 segment instruction pipeline, right? uh, 3 segment instruction pipeline. So fetch instruction, your ALU operation, and execute, these are the 3 segment, and assume that it will take 1 clock cycle for each segment. Now consider this 4 instruction. First is load the value into R1, right? Then load the value into R2. So first it will fetch the instruction, right? Then it will perform the ALU operation. So in this case, in this instruction, what will be the ALU operation? It will just transfer the value from memory to register. That operation will perform, right? And then the result will be stored into R1. Okay, same way for this. Now here the conflict will not happen, as we have 2 different buses, one for instruction, one for operand. So while the data is loaded from or transferred from memory to register, at that time this instruction can be fetched because we have 2 different buses. Then add R3, R1, R2, R3, store result of R1 plus R2 into R3, and then store that result, register result, into memory address at address 3, right? So if you see this, then the pipeline timing with this data conflict is like this. So we have a 3 segment IAE, this is the clock cycle. So first load R1, fetch, ALU operation, execute, fetch, ALU operation, execute, then fetch, ALU operation, execute, fetch, ALU operation, execute. Now what happened? This load R2, this is in execute fetch, and see here add R1 comma R2, that is in ALU operation. So what it will perform, this will store the result. So before storing the result, we want that operand. So R2, that will be stored in this clock cycle 4, but in that clock only we want to use this R2, right? So this is data conflicts because data is not available here, for this operation r1 plus r2, right? So what happened, that compiler will detect that and compiler will add this no operation instruction if it cannot reorder. So now if you see this load r1 load r2, this no operation means it will not perform anything, right? It just fill up a bubble in your pipeline. So now you can see that this load r2, that is to result in clock cycle 4, and this r1 plus r2, that operation is in clock cycle 5. So now that problem, data conflicts, that is resolved, here. Okay, so you can see that with the help of this no operation instruction, we have resolved that uh, data conflicts. So this is called a delayed load, right? This is called a delayed load. So it is wasting the clock cycle, one clock cycle, right? But we could resolve this data conflicts, otherwise you will get the wrong result. So that is not a good thing. So so this concept of delaying the use of data loaded from memory, that is referred to as delayed load. And the advantage of this is data dependency is taken care by the compiler rather than the hardware. It's a compiler, when converts your high level language into lower level language, it will do it for you. Okay,